Okay, so can everybody still hear me all right? Okay, so as I talked to a few different groups, I had a question came up about this problem 2 and how to use our knowledge of geometric series to determine whether or not these various series were convergent or divergent. And so I just wanted to talk through that really quickly. So first of all, jump in here. Right, so first of all, there's this question of what is a geometric series and how do we know if it's convergent or divergent? And so what we read about last time is that a geometric series is convergent. First of all, a geometric series is a series that can be written in the following form, right? So it's a sum, as some index goes from 0 to infinity, of an expression of the form c times r to the k. And the idea here is that c is just some constant number that you're starting with, and then the r is this common ratio. And so a series is geometric if it can be written in this form. And we see that, for example, in this first problem, problem 1, this is a geometric series because it can be written in the form. So this is the sum. This k goes from 0 to infinity. Notice I can just factor that 5 out, so the 5 is floating out front. And then the 3 to the k can be written as a 1/3 to the k, right? And so we see that this equation is the same as this equation, just written in a slightly different form, but written in a way that really highlights the geometric nature of this series. And so this is a geometric series. And once we realize that, the question becomes, does it converge? And if so, what does it converge to? And we saw in the video, the YouTube video, that in fact, this will converge. And it will converge to the quantity c divided by 1 minus r. Right, it'll converge to the quantity c divided by 1 minus r as long as that quantity r is less than 1. So in this case, right, in this case up here, we know that the r value is 1/3, that's less than 1, and so this should converge to 5 divided by 1 minus 1/3, which we can simplify down to 5 over 2/3, which is just 15 halves. Right, and so we see then that this series will converge to that quantity because it follows this formula here. All right, how does that sit with you all? Let me know in the chat. So then we get to these next few questions, right? These next few questions, these are also both geometric series, but there's this question as to whether or not they converge or diverge, and they look very similar to each other. The main difference being we have the 4/5 versus the 5/4, right? And so the real issue here is that in this case, we have c is just equal to 1. There is no extra c value, so c is equal to 1, and r is equal to 4/5. And so this will converge to 1 over 1 minus 4/5. That's 1 over 1/5, right? And 1 over 1/5 is just equal to 5. So that one will ultimately converge, while this bottom one sort of running out of room here. Notice for this bottom one, the C value is still equal to 1, but the R value is equal to 5/4. What does that mean about this one? So because the R value is not, 5, sorry, small mistake there. Not 5/4, that should be, not 5/5, that should just be 5/4. So because that R value is actually bigger than 1, this series will diverge. Right, and so we see that very sort of subtle change between the two will actually make a really big difference as far as whether or not the actual infinite sum converges or diverges. Ooh. Okay, I want to pause there for a second. How does that sit with everybody? Questions, concerns, comments about that? All right. Ooh, something in the chat. Yes. Good so far? Love it. Love it. Love it. Okay, so let's back out of this. Perfect. Awesome. So the next few problems, I should say, are very similar, except that they're written in this form, right? So they're written in this infinite, let me see, full screen mode. They're written in this infinite, what am I trying to say? They're not written in summation notation. They're actually written in this very longhand form. And so we have to first figure out how to rewrite them. And let's talk through one of these together, sort of briefly. Let's take a look at this bottom one. This bottom one's probably the trickiest one. So 5/4 plus 10/12 plus 20/36 plus blah, 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 plus blah, blah, blah. We want to recognize that this is a geometric series. And since it's a geometric series, or maybe I should say, first we just want to recognize that it is a geometric series. And to do that, we have to see what the common ratio is to get from one to the next. So how do I get from 5/4 to 10/12 and from 10/12 to 20/36 and so on and so on. And so let's take a look. To get from 5/4 to 10/12, I have to multiply by 2/3. Right? And then to get from 10/12 to 20/36, I also have to multiply by 2/3. And then to 40/108. Hopefully I did the math right, but I think that is also 2/3. And so on and so on. And so this series is really, it's 5/4 plus 5/4 times 2/3 plus 5/4 times 2/3 squared plus dot, dot, dot. Right? I guess next would be 5/4 times 2/3 cubed and so on. And so this is really equal to the sum as k goes from 0 to infinity of 5/4 times 2/3 to the k. Right? Where every single additional term we multiply by an additional factor of 5/4. And so we have this initial step where we have to recognize that this is a geometric series and figure out how to express it as such. But at this point, it becomes just the same as our previous problems, right? So once we know this is true, we know that in this case, we have our C value, that's our starting value, was 5/4. And our R value, our common ratio, is just going to be 2/3. And because that's less than 1, we know that the entire series will converge 2, and then we just have to do some math. This will become 5/4 divided by 1 minus 2/3. So that's 5/4 divided by 1/3. I want to say that's 15/4. So that infinite sum will actually sum to 15/4. Right, this is just using the same formula as before, which was C divided by 1 minus R, provided that R is less than 1. Yeah, Jose, you have a question?
Yeah, so how do you know the value of K? For example, on the problem like before that one, would it be K equals 1? Because it starts, since the rate is by 1/2 and it starts at 4. Or would that just be the...
Oh, I see what you mean. That's a great question. So the question, let me clarify. Jose's question is, what is the starting K value? And this is important because the formula for a geometric series specifically, right, the formula that we have written here, that's specifically for something of the form starting with a K equals 0 to infinity of an expression of the form C times R to the K. Right, so as soon as I start messing around with that, so as soon as I go from K equals 0, let's say if I plug in a K equals 1 instead, that's going to change the formula over here, right? The formula no longer directly applies. So we want to be a little careful with, there we go. We want to be a little careful with how our formula works. So how do we know what our starting K value is? So my secret today is actually that for all of these problems, I can always start with K equals 0. I just make sure that whatever my number here is, that is my starting C value. Because if I start with K equals 0, then the first term will always just be C times R to the 0. So that first term will just be a C. So in of these problems, I can just let C be whatever that first term is, and then I can let R be whatever the common ratio is. So hopefully this makes it clearer and less confusing. But for this problem, I could let C be that first value, and then R was the common ratio to get from one term to the next. Whereas up here, I could again let C be that first value, and then R would be the common term to get from one to the next, and so on. Does that make sense?
Yeah, that makes sense.
All right, great. Yeah, I love it. You also figured out how to raise your hand, which I'm so interested in. So there's a way in which we can raise our hand to ask a question, and that's so freaking cool. I'm sure, yeah, you all are smarter than me. You can figure that out. It's got to be something in the chat, maybe? Jose, how did you raise your hand?
I'm on my phone, so it's a little different, but on the computer, it should tell you.
Gotcha.
On the computer, it should tell you, though.
Gotcha.
Yeah.
Well, cool. Let me do this. I'm going to clear the drawings, and let's see what else we have to talk about here. Okay. Ooh. Okay, so there's a few more problems that we want to talk about, and I also want to be conscious of the time. I know that this class only goes until 9:15, and then, some of you might be going on to other classes. So I want to make sure you get out of here on time. Very briefly, how do we know that this series diverges? This is the sum as j goes from 1 to infinity of j over 4j plus 1. Just a few things to note. This is not a geometric series because it does not have the correct form, right? So it does not C times R to the K. Not a geometric series, but it's possible, right? Theoretically possible that it could be a convergent series that is not geometric. So how do we know definitively that it does not converge? Well, to see that, what we can do is we can use what's called the test for divergence. We can look at the individual terms, right? The terms of the form j divided by 4j plus 1. And we can see what happens to those terms as j goes to infinity. Right? And so as j goes to infinity, what we see then is that, so the terms are of the form j divided by 4j plus 1. And as j goes to infinity, we see the limit of those terms right? So what's happening there? As j goes to infinity, the limit of those terms gets closer and closer and closer to 1/4. Right? As j goes to infinity, the numerator and the denominator look more and more and more like 1/4. And so that means that the actual series, right? The series is an infinite sum. This looks more and more and more like the sum that's just 1/4 plus a fourth plus a fourth plus a fourth, and so on and so on. And so as j goes to infinity, these individual terms go to 1/4. That means that this becomes more and more like we're just adding 1/4 again and again and again. And so the whole thing just goes to infinity. The whole thing just diverges 1/4 of a unit at a time. So this was called the test for divergence. And we can say that since, let me actually, let's get a different color there. Right, so since these terms don't go to 0, since these terms don't go to 0, the series diverges. And that was the so-called test for divergence. I saw a couple hands up. So John, I think you had a question, and then Gabrielle, you might have a question. So John, you first.
I just wanted to quickly let people know like how to raise their hand. I figured it out. You just have to go to participants on PC, and then you should see the little option.
So you can, that's great. So did everybody catch that? So John said, in order to raise your hand on a PC, if you go to the participants window, you should be able to raise your hand from there. Is that right?
Yes, and they can also like say things like yes, no, go slower, go faster, need a break, clap. I can clap.
Cool. Okay, so there's actually a lot of different things you can say beyond just raise your hand. That's great. Thank you.
Let's stay clapping.
Gabrielle, do you have a question?
Yeah, I just wanted to check, how did you get 1/4? Because I can see a 4 in the denominator and probably like an invisible 1, or did you just like plug in stuff and...
Oh, that's a great question. Actually, thank you so much for asking that. Because, oh man, okay, yeah, I love it. Okay, getting a different color. Okay, so the question was, how did we know that this is equal to 1/4? The answer, our favorite, is that we can see this either through identifying that man, I'm stumbling over my words. Okay, 2 ways. Number 1, we can recognize that this is something like a polynomial divided by a polynomial in which both numerator and denominator have the same degree, right? So j raised to the first power. And since they both have the same degree, we can see this as a ratio of the coefficients. So the secret 1 out here divided by the 4 right there. And then in fact, that +1 really doesn't make a difference in the long run. But if we're uncomfortable with that, the other way that we can think about this is to use our old friend, which we'll try to spell correctly, our old friend L'Hopital, right? This is sort of like L'Hopital's rule. As j goes to infinity, this could be thought of as infinity divided by infinity. And then I could take the j derivative of the numerator and the denominator, and the j derivative of 1j is just 1, the j derivative of 4j plus 1 is just 4, and so this becomes 1/4. So we can also use L'Hopital's rule here. Love it. Thank you so much for asking that question. Anything else while we're here? All right, cool. Okay. So I want to end, and maybe I'll end a moment early here, but I want to end by looking at this problem and maybe solving one of these next few problems. We'll see. Well, at least we'll get through this problem here. So this is kind of interesting, and this goes back to something that Jose asked earlier. How can we use, and Jose was asking about starting with some value other than 0, right? Some value other than 0. So how can we use the formulas for geometric series and geometric partial sums to calculate what might happen if we started with some value other than 0? And so let me point out, I think there's a little bit of translation of notation here, but this is equivalent to the sum as k goes from some value to infinity of c times r to the k. Right, so using different letters, an a instead of a c, an n instead of a k, but this is the same idea. The idea is basically, if we're not going to start at 0, how can I compute this sum? And so this is very much in the same vein as what Jose was asking earlier. And so the answer is actually going to be this. We can use the formula that we've derived already. Whoop, just draw a quick line there. We can use the formula that says the sum as k goes from 0 to infinity of c times r to the k. And that formula was c divided by 1 minus r. But we also, and that's our formula for the whole series, but we also had this formula, right? We had the formula, this is the sum as k goes from 0 to m. Maybe, yeah, I'll say as k goes from 0 to m of c minus c times r to the m plus 1 divided by 1 minus r. So both of these formulas were given in the video. And in fact, we actually started with the second formula. We used that second formula to figure out the top formula, right? We let m get bigger and bigger and bigger, and we let m go to infinity in the second formula to get the top formula. And so it turns out we can actually use both of these formulas together to help us figure out this top formula. And we're going to do this as follows, right? First, I'm going to recognize that if I have this expression, this is adding up infinitely many things, while this expression is just adding up the first m of those things, then I can basically take this formula and subtract this formula to get this formula, where we just have to be a little careful with the indexes, right? But in other words, if I'm adding up from the 0th object, infinitely many objects, and this gives me the first m, then to get this expression starting with m and going forward, I just have to take something that looks like this, and I have to subtract something that looks like this. Okay. But let's try to be a little more precise. So what I want to observe, first of all, is that if I'm taking a sum as k goes from m to infinity, that is like taking the sum as k goes from 0 to infinity, but then I subtract the first certain number of elements. So I'm going to subtract the first number of elements as k goes from 0 to m minus 1, right? If I want to start with the mth element, like I do here, I would have to subtract the first bunch of elements up to the m minus 1 element. That would let me start with k equals m. And so if I want to do that, then I'm going to need to be able to get a formula as k goes from 0 to m minus 1. Right? And so to do that, I'm going to get this formula down here. That plus 1 and that minus 1 will cancel each other right out. And so that will become c minus c times r to the m over 1 minus r. And so taken together, right, the formula that we're working towards, we've got this expression here. So we want to take the big expression minus the smaller expression. That will be this expression minus this expression. And so that ends up being, draw a line here. So we end up getting that the sum as k goes from m to infinity of c times r to the k is equal to c over 1 minus r minus c minus c times r to the m over 1 minus r. Right, and then that simplifies. We have the common denominator of 1 minus r, and then we just end up with a positive c times r to the m. Right, so in a way, Jose, this is a different answer to your question from a while ago, that if we end up starting with a value other than m equals 0, this is what we can do. This is the formula we can use.
And can you tell me again why it's m minus 1? Is it because it cancels the 1?
You mean for this right here?
Yeah.
So the idea there is that if I want to start at the mth element, I have to eliminate all of the elements that came before that. So if I want to start at the mth element, I have to eliminate all of the elements up to and including m minus 1. So I can then start with the mth element and go forward from there.
Okay.
But ultimately subtract off all of the elements from 0 up to m minus 1. I have to eliminate those first bunch.
But why minus 1 specifically? Why not plus 1 or minus 2, you know?
Because each of these numbers are really counting numbers, right? So 0, 1, 2, 3, ... M is some counting number, and the counting number that comes right before it is m minus 1, right? So if m was 100,
Okay.
right, if I wanted to start with the 100th element, I'd have to eliminate the first 99. So whatever m is, eliminate up to m minus 1.
Oh, I get it. Okay. And then subtract that.
Right. And then subtract that.
Yeah, makes sense.
Perfect. Okay, so I want to pause there because we are just about out of time. So I'm gonna stop the recording really quickly. See if I can figure out how to do that.